Hello, everyone. I'm Satish. I'm here on behalf of the Young Researchers Activity Team of the International Society for Quantum Gravity. Today, we have the third of the three lecture series by Giulia on quantum gravity phenomenology. Right? In the first lecture, we learned about some rudimentary aspects of quantum gravity phenomenology, right? So, how to build models. You have like theories completely removed from reality. And we have few things we can measure in experiments. So how do we connect those two, right? So you have to look for the part of the theory where you can write down something that can be tested, right? So it was mostly, in many ways, it was the dispersion relations, right? And other things as well. And in the second lecture, we learned about how to use different cosmic sources. We get our information from either, sure, light, right? So, and then neutrinos, GRBs, gamma ray bursts, right? And primordial gravitational waves. That's what we learned in the second lecture. And let's see what Julia has for us this lecture. Thank you, Julia. Um,
Thank you, and thank you for the summary about the first two lectures. So before we start, let me ask if there is any question concerning what we discussed before. Okay, apparently not, so we can...
we're good, we're good.
Okay, so we can continue. So, oops. Okay. So the plan for this last lecture is to discuss in more general terms the fate of relativistic symmetries in different quantum gravity, quantum spacetime models, and also how to distinguish them using phenomenological considerations. Then I'm going to discuss a different regime, let's say, of quantum, well, a different point of view on quantum gravity phenomenology, namely the possibility of having infrared ultraviolet mixing. And I will, well, let me not say now what this is about, I will say it later. And then I'm going to discuss a somehow more recent line of research in phenomenology, namely studies of effects of quantum gravity in quantum systems. And as an example of this, I will discuss the coherence. Okay, so let's start with relativistic symmetries. So in the previous lecture, as you mentioned, we talked quite a lot about the modified dispersion relations and some ways to test them. In that lecture, I had linked them to a specific model of non-commutative spacetime, but I was also remarking that that was just an example. It's not the only way to have such a modified dispersion relation. And now here, I want to discuss a bit more in general, what can we say about model building if we want to have a modified dispersion relation. So say that at some point we are able to confirm that at Planck scale the dispersion relation is modified. This is just a work hypothesis. Then regardless of the original theoretical motivation where we took that formula from, we want to study more in general what can we say if there is such an effect. And of course, this brings us to discuss the fate of Lorentz symmetries in quantum gravity models. Um, of course, if you have a modification of the dispersion relation, in most cases, it will be related to a departure from relativistic symmetries, unless in very specific forms of the dispersion relation. So in general, what can happen to symmetries? Well, they can be preserved, so we can have standard local Lorentz invariance at the Planck scale. This would be the most conservative scenario. Then we can have the case in which symmetries are broken, namely there is a preferred frame. I see there is something in the chat. Why Lorentz invariance should be preserved. So here, well, I will discuss in the next slide what different fundamental quantum gravity theories have to say about Lorentz invariance. Here, the approach I want to take is a model agnostic point of view. So say that at some point we are able to confirm that there is such an effect, then as phenomenologists, what are we going to do? We are not going to jump on the first model that we see and link the observation to that model. We want to really understand exactly what that specific observation is telling us in general. Okay, so how do we build models and constrain different models? So as I was saying, the second option is that there is a preferred reference frame. This would be very similar to what people used to think about when there was the puzzle about speed of light when electromagnetism was developed. At the time, people thought, oh, this is the speed of light in a specific frame that is linked to some ether. And then in moving frames with respect to that one, we should measure a different speed of light. Then people did experiments, famously the Michelson and Morley experiments, and they found that the speed of light was invariant regardless of the speed of the reference frame. So they had to figure out something else, and this is how special relativity was born. And similarly here, you can, besides the Lorentz breaking scenario, then you can have another scenario where there is no preferred frame, and what is different is the laws that link different inertial observers. And this last scenario would be the one that applies to the model, to the specific model that we discussed in the last lecture. I mean, that is one example of a model with deformed relativistic invariance. It's not the only one possible, as I mentioned already. Then, of course, any of these possibilities that we have here have different observational consequences, even if some of them may agree on the form of the dispersion relation. And the specific other consequences, well, there are some that can be general, as I will discuss, but some others depend on the theory within which we are embedding these models. We may have different assumptions concerning the dynamics, different assumptions concerning the Hamiltonian description of the system, and so on and so forth. We can have really many things. So this is to say that once we see, if at some point we see a specific effect, or if we constrain a specific effect, then we have to make clear what is the full set of assumptions that we are either confirming or disproving, okay? So concerning what can we say from the fundamental quantum gravity theories that we have available? In fact, it's not always easy to know what the theories say, because local Lorentz invariance has to do with the semi-classical limit of the theories. So it is not always possible to do a rigorous derivation and see what happens. However, we can make some guesses. And for example, we have that string theory is in principle Lorentz invariant. However, you can have a breakdown of the symmetries when there are extra tensor fields in the theory, which is a possibility that has been considered. In loop quantum gravity, there are some indications that Lorentz symmetries might be deformed. And these indications come from example from looking at the hypersurface deformation algebra, which tells you basically what are the symmetries of the theory. Another example is causal set that has as a built-in feature Lorentz invariance because of And this has been implemented from the beginning in the construction of the space-time atoms that are the basic building blocks of the theory. In non-commutative geometry, depending on the model, you may have a breakdown or a deformation of the symmetries. And as I mentioned in the previous lecture, we had seen an example where you have a deformation, but you may also have theories where symmetries are broken. And then another example is Orava-Lifshitz gravity that has a built-in Lorentz where Lorentz is broken from the beginning because you have preferred time foliation in the ultraviolet regime. So you see that you may really have. I mean, this does not is not a complete description. Of course, it doesn't have that. I mean, you can think of other things. However, I mean, this is just to tell you that there are many options, so it's worth to consider all the options. Now, again, I mentioned this already. Let me just say it a bit more clearly. I'm not going to discuss the Lorentz invariant case because that is what we are all used to, so it doesn't need more discussion. However, I want to compare here different implications of theories with Lorentz breaking and theories with Lorentz deformation. And again, what I'm going to discuss here is going to be independent of the underlying theory, okay? I'm going to make some general considerations, and if I mention a specific embedding in a theory, I will say it explicitly. So when you have a breakdown of Lorentz symmetries, the laws that link how different observers see the world are the ones that we have in special relativity. So everything transforms as usual under the Lorentz group. However, there is a preferred frame where the laws that you're interested in take a specific form. And one example is about how this could happen is if you introduce some fixed background tensors in your theory. Here, just as an example, there is a scalar field action, and you see that besides the standard metric, oops, sorry, I have to, many apologies, I have something ringing and I don't know what it is. Many apologies about this. Let me. Okay, done. Many apologies. I forgot to deactivate all notifications. So I was saying, in this case here, you have the usual metric, and then you have an additional tensor that you can think about as a fixed background tensor. And this is what is giving you your preferred reference frame. So you see that in this theory, you have formal covariance, meaning that the indices are saturated as usual. However, when you describe things from the point of view of different observers, then you will make different predictions. And as I mentioned, the typical manifestation of this is exactly having modifications in the dispersion relation. Now, in theories where Lorentz symmetries are deformed, all observers agree on the laws of nature, so they would describe things all in the same way. However, when wanting to change reference frame, you have to account for the fact that the transformations are deformed. And I will discuss this example in a second in a bit more detail. Now, as I was saying, let us assume that we have some reason to think that, in fact, we see a modified dispersion relation at the Planck scale. Then what can we say in the Lorentz breaking scenario? So we can stick to a pure kinematical level to begin with, so not consider dynamical properties. At this level, we don't have constraints. In principle, we don't have constraints on other features of the theory. However, for example, there is no reason to assume that the laws of conservation of energy and momentum are modified. Okay. So, for example, let us complete our kinematical model by adding to the modified dispersion relation also standard conservation rules in interactions. For example, here I'm going to consider the case of a modified dispersion relation for photons and electrons that take different form, but with possibly different values of the parameter that is governing the amplitude of the effect. Now, if you do this, so you combine a modified dispersion relation with the standard conservation laws, what you typically get is that you have very strong effects on threshold reactions. Okay, so say that you have a reaction that can only happen at some threshold. Typically, this threshold will be modified in a substantial way in this scenario. And in particular, something that may happen is that, for example, it may be possible for a photon to decay in vacuum. So you know that this is forbidden in special relativity because such a process would identify a frame, which is the frame where you have where the photon has enough energy to do the decay. Okay. And in fact, what you can do is you can do the usual kinematical analysis, and you can derive a constraint that tells you whether this process is allowed or not. Now, here I'm writing the constraint already in the modified theory. And you see, in fact, that we have the eta and the xi parameter. However, if these are zero, then you have the standard special relativistic scenario. And you see that the standard case would be that this quantity, where theta is the angle between the momenta of the electron and positron that are produced, would be equal to zero. And in order for this relation to be satisfied, you will need to have that the cosine of theta is larger than 1, which is not possible. So this is what mathematically tells you that the reaction is forbidden in special relativity. However, once you introduce such a modification here, you have a modified condition, and there is a region in the parameter space of the theory, so in the energies of the particles involved, where the reaction would be allowed. And of course, once you have a modification of thresholds that are these are very visible things. For example, a process that is usually forbidden and suddenly becomes allowed, it is something easy to constrain, right? And in fact, such a process, for example, has been constrained strongly with observation of ultra-high energy cosmic rays. Before going on here, I want to make a note, which is what is written here at the bottom. So if a process is allowed at the kinematical level, it may still be forbidden at the dynamical level, right? Or it may be suppressed at the dynamical level. So if we don't see the process, okay, doesn't mean that the kinematical model is excluded. So the kinematical model predicts a process. We don't see it. Can we say that the kinematical model is excluded? No, because it might be a dynamical effect that is hiding the process, right? So we have to be, this is one example where you see that one has to be really careful about stating the assumptions that are behind the model that one is testing. Yes.
Maybe it's too early to ask this question. Like maybe a lecture ago, somebody asked this question. I don't know, maybe it could be Saulo, that how do you lift the degeneracy? Because many theories lead to the same dispersion, same kinematics, right? So that way we don't know if it's coming because of the time-preserving foliations in Horowa-Lipschitz or because of some effects in loop quantum gravity, this kind of things, right?
Mhm.
Does this kinematics, dynamics, is it going to help you discriminate between those things?
Uh, yes, I mean, the more
Kinematically,
ingredients, I
they're
mean,
all,
some
they
theories may have a similar kinematics, but then have a different dynamics. So this is when, I mean, you need to, this is why I say that you need to look at everything
Mhm.
to discriminate between the theories. It is very likely that if we ever see anything, I mean, not necessarily a dispersion or a modified dispersion, anything, it will be a very simple phenomenological model, and it will not tell us immediately which theories are good and which theories are bad. However,
Okay, so
once you have information from nature, be it a positive information or a negative information, so either you see or you constrain something, then you have a very strong anchor on which you can base your construction of a theory, you know. So if you say you don't see photon decay, we don't see photon decay. So we know that the theory we want to build has to be a theory such that either because of the kinematics, either because of the dynamics, or for any other reason, is not allowing that process, okay? Or conversely, if you see something, then it has to be a theory that allows for that process. So this is exactly the point. I mean, you pinpointed the take-home message of this part of the lecture. It's exactly this. You have to start from what you see and slowly build up, adding ingredients and seeing which ingredients are compatible or not with what you are observing. But I mean, it is very unlikely that you will have a full-fledged model and then you will see exactly something that you can ascribe to that model. Probably you will see something that has many different possible explanations, and then slowly you build up on that. Okay.
so all we give to the observers is this kinematic relationships, and they go find something and they measure the deviation. Perhaps the size of the deviation is dictated by the dynamics, right? So maybe this much is not allowed by loop quantum gravity. Maybe this is too small,
Yeah, it is
something
the
like this, right?
size, but also once you have that, then you can start saying, for example, in this case, you assume you see a modified dispersion relation. Then you say, okay, if it was a Lorentz breaking model, then I would also see modified threshold reactions. Do I see them?
There,
No,
yes,
they are
yes.
strongly constrained. Then what does it mean? That if I want to have Lorentz breaking, then I need a dynamics that forbids those processes. If I see them, then okay, I am I need a dynamic that does not hide those processes because I am seeing them. So you see, and very slowly
Right.
you build up. And at the same time, who is working on fundamental theories has like an objective where eventually the theory has to get. So it's really a two-way process. So, for
Yeah.
example, uh, this goes very well with your question. So, say that we want to learn about, we want to implement also some dynamics in a Lorentz breaking model. And the most conservative way to do it is to use effective field theory. So you take your standard model, the one that we know, and you add additional operators that break Lorentz symmetries and preserve everything else. For example, gauge invariance and so on. Within such an effective field theory, if you want to have effects that are suppressed by the Planck scale, then you need to introduce operators that are non-renormalizable. So operators that have a mass dimension larger than 4. Okay. And you say, okay, I want to do to embed my model in this theory. So I take the QED Lagrangian and I'd add the mass dimension 5 operators because these are the ones that will induce a linear energy dependence on the velocity of photons, okay? It turns out that the most general thing that you can write is this one. I'm not going to demonstrate it, but this is a well-known result, where you have the Lorentz breaking is given by a 4-vector and mu, that is a fixed background vector, and then you have psi and z that are dimensionless parameters, analogous to the eta or psi that we have here. Now, if from here you work out what dispersion relation you get, you will find that for photons, it is dependent on the helicity of photons. So it's not that all photons have a correction with a plus sign here or a minus sign. Depending on the helicity, you will have opposite corrections. So in this case, if you want to embed your model within such a theory, then you know that there is this effect. This means in particular that you have birefringence, namely that if you have a source that is emitting linearly polarized light, then the direction of this polarization will rotate as the light propagates because of the different phase velocities of left-handed and right-handed photons, okay? And this is something that, in fact, can be constrained, and it has been constrained, for example, using observations of the Crab Nebula, or even using observations of the cosmic microwave background. Here I'm only putting this reference where you can find a lot of references of previous work. There has been a lot of work on this. So you see that if you want to use this dynamical framework, then you cannot have a simple modification of the dispersion relation like the same for all photons, but you will have this slightly different effect. So you would need to account for this. So this is another example about how you can distinguish different scenarios. Now let's go to the deformed symmetry scenario. I'm going to go fast on this because we already saw a specific example, so we don't need to do everything again. But the general idea is that if you have a modification of this kind, then you have a very specific form of the boost transformation such that this thing is invariant, okay, meaning that a boosted observer, so if I boost all the momenta and all the energies, will write exactly the same relation. And then if I want to complete the kinematical model, I have to also deform the laws of conservation of energy momentum because I want them to be invariant under the new transformations as well. And for example, and this is one example of laws that are compatible with this boost transformation and this modified dispersion relation. Now, what happens in these kind of models? If you look at the interactions, so I mentioned that in the Lorentz breaking, you have very strong effects on interactions. In this framework where symmetries are deformed, you have much smaller effects on interactions. And this is basically because once you constrain everything to be relativistically invariant, you don't have very strong departures from the special relativistic theories. For example, a photon decay process of the kind that we have seen previously in the Lorentz breaking scenario is not possible because, again, photon decay would identify a preferred frame. If the theory is invariant, even though invariant under deformed transformations, you cannot have a preferred frame. So the biggest departures from the special relativistic theory are forbidden. More general threshold reactions, so reactions that already in special relativity happen only above some threshold. So in this case, the thresholds are modified, but they are modified typically in a much less in a much weaker way with respect to the Lorentz breaking scenario. So they are also harder to constrain or harder to see. Typically, what happens is that you would see a modification in the interaction only for particles that are already close to the energy, to the quantum gravity scale. So you would see them for very high energy particles that we don't observe directly. Then, if we want to discuss dynamics in these models, things become already more complicated than what happened for the Lorentz breaking scenario, because we still don't have an established dynamical theories for these models. We have, in some cases, for example, for some specific forms of space-time non-commutativity, we are able to write down a field theory. But we are not able in general. So at the moment, I can't really give you definite statements about what the dynamics in deformed relativity scenarios is. Also remember that what we mentioned in the last lecture is that it is very typical in this kind of models that you have a relaxation of the locality principle, right? You may remember that we mentioned that you have that locality is relative to the observer. This means that if you want to write a field theory, you will have somehow to embed this modified realization of locality. Okay, so there are, here we are getting to the boundary of where the model building is at the moment. So dynamics is not really well developed yet. But still, even if you don't have dynamics, so if, for example, photon decay is forbidden, as we said, there is not going to be any dynamical process that makes it allowed. So we are not going to see this kind of processes. And yeah, as I mentioned, probably to describe such a framework, we need to go beyond the effective field theory framework. So this is something difficult that people are currently working on. Another way to, another aspect where you can distinguish the two frameworks concerns the very observation that you may have used to establish that there is a modification in the dispersion relation. As I mentioned last time, when you want to analyze the difference in time of arrival of particles with different energies, you have to account for the universe expansion, right? And typically, what you use is a formula of this kind, where, yes, you have the Planck energy suppressed term, but then you have an effective distance that depends on the redshift of the source. Now, this formula here was derived by Jacob and Piran. I forgot to put the reference. I will add it before publishing the slides in 2008. And the assumption that led them to this formula was that the energy is affected by redshift in the usual way as the particles travel. If you are in a Lorentz breaking scenario, this does not need to be the case any longer. So the fact that energy transforms in this way in an expanding universe is due to the invariance properties of your theory. If you're breaking them, then you may consider any other relation between the energy of the observed signal and the redshift of the source. So, I mean, here is one example, but in principle, you have infinitely many possibilities, right? Which would be, which is a problem when you want to constrain something. What you would need to do would need to get constraints at different redshifts and see how the thing evolves, how your signal evolves with the redshift of the source. When you are in the deformed relativity case, you see again the effect the constraining power of your relativity principle. So instead of having an infinite array of possibilities, what you find is that if you want consistency with the symmetries of your model, you basically only have 3 free parameters, which are already a lot. I mean, 3 free parameters for a very small effect are already very difficult to constrain. I mean, what I hope I convinced you about in the last lecture is that already having just 1 free parameter is really, I mean, already just with 1 free parameter, it's really hard to constrain the model. And what we were discussing in the last lecture was a case where you only have this eta1 parameter here. And in this case, you recover the formula that I showed you last time. But in principle, you can have also these other contributions. And here, this is just a plot of what happens if you turn on one of these parameters at the time. So this is for eta1, which is the case we were discussing last time. This is for eta2, and this is for eta3. And you see that you have, I mean, if you combine these 3 things, you can get many possibilities. Here, I just want to show you a couple of examples that are interesting. This one is interesting because you see that basically you would have, this is a plot of the time of arrival difference versus the redshift of your source for some probes of a fixed energy, okay? And you see that, so the dashed line is what we have been testing. This black line here is a case where at very small redshifts, you basically have no effect. And then eventually your effect starts to increase a lot, and then it stops increasing and it decreases again. So this is something to test this thing. For example, you would need to go at high redshifts to see something. You wouldn't see anything at small redshifts. This one is interesting because you have an even stronger, even stranger effect, namely that at small redshifts, you have that particles with higher energies arrive earlier, and then at higher redshifts, you have particles with higher energies arriving later. So you have a change of sign of your time of arrival difference. So again, to test such a thing, you would need to really have observations at different redshifts. In any case, at the moment, it's good to know that there are these possibilities, either these or even the more general Lorentz breaking case. We don't have the sensitivity to test these specific models at the moment. At the moment, we are still investigating the possibility that there is the effect in general. And we use as a test case, as a benchmark, let's say this formula here. It's good to know that there are other possibilities, for example, because we need to know that there may be no effect as more redshifts, and we may need to go at higher redshifts. But yeah, I mean, understanding the specific form of the effect, if we at some point convince ourselves that the effect is there, is going to be a whole new business, okay? And yeah, this was to, on the one hand, to show you another way where just having the form of the dispersion relation is not enough, and you need to say what is your more general model to really know what you're looking for. On the other hand, is to show you that even such a very simple test has already a lot of complexity at the modeling level. Okay. So I would stop the discussion about symmetries here. So before going to the next topic, let me ask if there are any questions on this. Okay, I don't see anything in the chat.
Since there is, and I'll ask a quick question. So, what if, in this case, the photon we are talking about, if it is from the CMB, does it explain in any way, kind of like a Hubble tension kind of thing, right? So, because there is a very strong redshift dependence, and also it changes. Intermediate is different from close by and very far away, right? So, can you say something about this? But it's
I wish I could
two
say
different
something.
problems.
I
Okay,
wish I could say something. I
okay,
can't because it's really something that has not been explored as far as I know. So I cannot comment. I mean, in principle,
okay.
it is interesting to see if anything of this sort could affect cosmological observations of that kind, but I don't know at the moment. I mean,
Okay.
from what I know, this has not been really discussed in the literature.
Yeah. I haven't seen that either,
But
but I
it's,
got the
I
idea of
mean,
this.
it is an interesting question, something worth thinking about.
Julia, there's a question in the chat.
Yes, let me open. What are possible hypotheses that would make you turn on or off these parameters? So here, as I said, if you have a full-fledged theory, then the theory will tell you what these parameters are. So which parameters are on, which are off, and what is their magnitude. Here I'm taking the perspective of a bottom-up approach. So what are the, I am exploring what are the possibilities within very general frameworks, namely the framework where symmetries are broken and the framework where symmetries are deformed. At this level, there is no constraint that tells you which parameters have to be on or off, apart from observational constraints, right? So the fact that in this deformed symmetry scenario, you only have 3 parameters is a constraint that comes from your modeling, because it comes from the fact that you want to preserve symmetries. And in fact, if you don't preserve symmetries, so you go to the broken symmetry scenario, then you have an infinite number of parameters. Okay. But from this perspective, there is nothing that can tell you. I mean, from the perspective of wanting to do the phenomenology, I have to be aware of what are the possibilities within a given framework. And then, yes, I want to hear from people who are developing fundamental theories. I want to hear from them what they have to say about these parameters. But at the moment, this information is not really, this is not something that people have looked into. So I can't tell you this theory turns on this parameter or that theory, that parameter. Another question? Oh, no, okay. Okay, I think we can move on to the next topic. Oops. Okay, which is infrared ultraviolet mixing. So now we are going to go a bit back to the spirit of our first lecture, where we want to understand from general considerations what can be possible features of a quantum gravity theory, okay? So there are cases where you introduce an effect, quantum spacetime effect or quantum gravity effect in the ultraviolet, which is what you usually want to do if you're doing quantum gravity. But then this effect has within the theory is such that the effect has a counterpart in the infrared, so in the very low energy or very large distance regime. And you all know about one example of this, which is the entropy area law of black holes. So you know that the Bekenstein-Hawking entropy bound for for the entropy, well, it tells you that if you have a region of size L, then the entropy goes like the area of the region. So it goes as L square, where L is the linear size of your region, divided by the Planck length square. But you also know that in quantum field theory, you can count the degrees of freedom of your theory. And if your theory has a ultraviolet cutoff lambda, then the entropy will be lambda to the cube, L to the cube. So the entropy typically goes like the volume. And well, the result about the entropy for black holes was really an important result, because what it's telling us is that there is a mismatch between what is happening for black holes and what we are told by quantum field theory. And this mismatch becomes more significant when we increase L. So when we go towards larger length scales. And in fact, it becomes, it increases and it becomes significant when the size of the region that you're looking at is larger than this combination of the Planck length and the ultraviolet cutoff. And some people have used this to argue that, for example, Cohen, Kaplan, and Nelson have used this to argue that there may be a cutoff infrared scale for effective field theory. So effective field theory may not work in the far infrared. So this is a very well-known example where there is a balance between the ultraviolet and the infrared features of a theory. If we go more within quantum gravity studies, you have another example which comes from putting together the Heisenberg uncertainty principle and the variation in mass of a black hole when it emits radiation. So the general argument is that if you want to localize a black hole, you may look at radiation it is emitting with a given wavelength, namely a given energy. But at the same time, when the black hole is emitting, this radiation is changing its mass by a given amount. And if you put these things together, you get a modification of the standard Heisenberg principle. So you have that your uncertainty in position, well, it has the usual inverse dependence on the momentum that comes from Heisenberg, but then it has a linear dependence on the momentum, which comes from putting these two effects together. And so you see that when you go to the ultraviolet, namely when you go to high momenta, you have an infrared uncertainty in the position. So again, you have that the two regimes are talking to each other. And we also have, well, we have many examples. Another one that I want to mention because it falls within the non-commutative models that we have mentioned in here and there as very good toy models for different features. So consider a non-commutative spacetime of this kind. So the non-commutativity between x mu and x nu is given by a matrix theta mu nu. From here, you derive an uncertainty principle of this kind in the usual way. And you see that what this is telling you that if you're going into the ultraviolet with the nu coordinate, so delta x nu is going to 0, then correspondingly you will have that the mu coordinate is going to infinity. So there is no way to go to study a pure UV regime in this spacetime, because when you try to go UV in one direction, you will go infrared in the other direction, and there is a balance between the two. And this is also seen when so this kind of non-commutative spacetime is one of the few examples where we know how to do quantum field theory. I mentioned earlier that in general, we don't know how to do it, but in this case, we know. And if you do quantum field theory on this spacetime, for example, you want to study a simple theory with interaction of the kind lambda phi to the fourth, then you get that your propagator has an additional term with respect to the standard propagator, which I mean, said in very simple words, comes from the fact that when you do loop diagrams, because you have non-commutativity, you may have non-planar loop diagrams. And so you get contributions that, as you can see, become relevant for small values of the momenta, okay? So you have a theory that, besides having the usual ultraviolet cutoff, also has some infrared divergences. And this kind of propagator can be used to derive a dispersion relation. And here you see it even more clearly. So you have the standard terms. Then you have a term that is diverging quadratically with the momentum when momenta are small. And then you have another term that is, again, diverging where the momenta are small, however, is diverging only logarithmically. So this is a soft infrared divergence. And well, in fact, this term here, you can show that, I mean, you can show that when you have momenta that are smaller than the mass, this is the one term that is more relevant. So this soft divergence. But I mean, the point here, I don't want to go into all the technical details. The point here is that you have a theory where you have that your ultraviolet scale, which in this case is theta, because theta is what is here. So your ultraviolet scale is inducing a divergence, not in the UV, but in the infrared, okay? So this is an example of this ultraviolet infrared mixing that I was discussing. And it is very interesting that in recent years, people have been thinking about the possibility of using this model as an inspiration for building very simple scenarios, simple phenomenological models that can be tested experimentally. So again, this is what people doing phenomenology want to do. They get inspiration from either general arguments or from specific theories and develop models that can be tested. And one example that was proposed a while ago concerns cold atom interferometers. So cold atom interferometers basically are systems where you have atoms with the momentum that is smaller than their mass, and they interact with photons and have a slight change in their momentum. And so you are in this regime where this kind of modification would be relevant. And in fact, you can parameterize the energy momentum dispersion relation for these atoms in this way. Notice that here you have a term that is written, this is for the small velocity limit of special relativity, okay? Because we have small momenta. So you want to test this, and you ask yourself, what happens if in these atom interferometers, I account for this kind of dispersion relation for the atoms? Now here, with respect to other cases that we have discussed, where we had something that was amplifying the effect that we could see, right? For example, for the time of flight studies, the amplifying factor is the large distance that is traveled by particles. Here you don't have an amplifying effect. However, you have an experiment that is incredibly precise. So it can be used to test even tiny effects. In fact, this kind of a test of experiments with the cold atom interferometers are usually used to measure the fine structure constant alpha, okay? And here you can see this is a measurement done with the atom interferometers using cesium atoms. This is a measurement done with atom interferometers using rubidium atoms, and this is the measurement that is done in a more standard way with the G-2 for constant for the electron, which is what people do at particle accelerators. And you see that the precision is really comparable with what you can do using particle physics experiments. So it's really an incredible precision. And you will also notice that here that currently there is a mismatch between what is seen using cesium atoms and what is seen using, well, rubidium and electron G-2 are consistent measurements. They are within 3 standard deviations, so you can combine them. But you see that there is a large mismatch between this and this. And in fact, what it has been shown in this very recent paper is that you can use this mismatch to measure the parameter L. So to measure the parameter that is giving you the deformation, the infrared deformation of the dispersion relation. And well, the details are in the paper. I'm not going to give them all, but from this mismatch, the measurement that you get is that L should be 0.6, around 0.6 times the Planck length. So this is super interesting for 2 reasons. One is that this may actually be a case where we are seeing an effect of quantum gravity. But more conservatively, this is super interesting because we are seeing that these experiments that are tabletop experiments nowadays are so precise that we can go to test Planck scale effects. Okay, so this is, well, in the previous lecture, we saw that time of flight studies for astrophysical particles give us Planck scale sensitivity, right? Which is already a big thing. So discovering that you have a physical framework, an experiment that you can do that allows you to reach that sensitivity is already something incredible. And here, this is very relevant because we have found another physical framework that is completely different, that again allows us to test Planck scale effects, okay? And another consideration that I want to make here that will also bring me towards the transition to what I want to say next is that you see that if we have several experiments with Planck scale sensitivity, and these experiments concern very different regimes. So we discussed the running dimension last time, and that is a very ultraviolet effect. And in fact, to test it, perhaps we have to go to the primordial universe where we have really Planck scale physics. Then we have seen an example, which is the time of flight studies, where we are studying the residual effects of ultraviolet features of the theories. But we see them at low energies because, well, at relatively low energies because we have some amplification mechanism, okay? And this one is an example of another framework where instead we are testing the extremely low energy, okay? So these are cold atoms. So it is really different regimes. And you really want to have a collection of these kind of observations that you can make, because then you can really constrain different corners in your parameter space. So you remember that I was showing this cube during the first lecture, saying that you want to test different ways to depart from the full quantum gravity regime. And well, the spectral dimension may be somewhere around here. Then we discussed modification of kinematics. We would be somewhere going towards special relativity. And I mentioned in the first lecture, and now I want to discuss a bit more in detail, that another thing that we can test is quantum gravity effects going in these directions, so going in the direction of quantum mechanics. So they will show up as modifications of the behavior of quantum systems, okay? And in some sense, this example here of the cold atoms is something going in this direction, okay? And so more in general, what can you hope to test in this part of the parameter space? So one thing that has been studied for a long time is quantum mechanics in curve background. Okay, so you have classical spacetime, perhaps with curvature, and you consider quantum matter on this spacetime. This is, I mean, this has been studied for a long time, but still it's giving you information about one limit of your quantum gravity theory. And within this context, for example, already in the 70s, people were studying how the Schrödinger equation behaves in the gravitational field of Earth. And they showed that they were doing, again, atom interferometry in that case, and seeing what was the phase difference induced if two atoms were traveling at different heights in the gravitational field of the Earth. And they demonstrated that you can write the Schrödinger equation with the Newton interaction term, that is the interaction between the particle and the gravitational field, in the most straightforward way you would do it. And what they were observing was matching these kind of observations. And this experiment has been refined in the following years. So we are quite confident that if the gravitational field is weak, then the quantum particles living on it, their behavior, their dynamics can be modeled with the Schrödinger-Newton equation. Another thing that people have been thinking about for a long time is the possibility that the interaction with the gravitational field induces the coherence in quantum systems. And I will say more about this later, so I don't want to go into details now. People have been studying also the quantum equivalence principle. Namely, people are asking themselves, we know that the equivalence principle holds for classical bodies. So I have classical particles, planets, whatever, they obey the equivalence principle. But what happens to a quantum particle? It's not obvious that the equivalence principle should work for a quantum particle as well. And people are considering this option both at theoretical, at the level of theoretical modeling, and also at the level of thinking about how to test this. Well, and then for a very long time, people have been developing quantum field theory in curved space-time. On this, I think you even have a very dedicated lecture course, so I'm not going to say much. But anyways, this is one framework where you are going in the direction from quantum gravity to quantum mechanics. Another framework is the one where you ask yourself, what is the gravitational field generated by a quantum system? So while here you were not considering the fact that the quantum particle also is a potential source for a gravitational field, but you were only considering the effects of a given gravitational field on the quantum particle, then you ask yourself, how does space-time geometry change, or space-time properties change due to the presence of quantum particles? And well, this is a question that people have been thinking about for a long time, because it's relevant in the early universe physics. And in fact, and the first thing that had been proposed is that, okay, you have quantum matter, you take some average over some state, and this is what is sourcing your gravitational field. It is one option, even though you have to be very careful about how you define the state of your matter field in order not to have inconsistencies in this equation. And in general, it is not really satisfactory because, yes, you are, I mean, you need very specific conditions on here for this to work out. But I mean, it is one of the possibilities that people have been considering. Recently, people have been thinking about, can I measure the entanglement of two quantum particles generated by the respective gravitational interaction of the two quantum particles? So we know that if two quantum particles interact, for example, via electromagnetic field, there will be an induced entanglement. We don't know if a similar thing can happen if the two particles only interact gravitationally. This is something, again, that people are studying at the theoretical level and also at the level of devising experiments to see this. So this is really, here I am trying to give you a flavor of what are all the possible directions. I can't go in details about all of this because it would be really too much. It is a very interesting field at the moment for the phenomenology of quantum gravity, and is a field that for which people have realized the interest from a quantum gravity perspective in relatively recent times. So I think it's, I mean, at the moment, many things are still under study, under development, but I think it's something to look forward for news, and it's something worth also thinking about. And then a third thing that you can do is to ask yourself what is the behavior of a quantum system in a quantum spacetime. So it's one step, an additional step forward. Here you have the given gravitational field. Here you are considering the possibility that perhaps a quantum particle will generate a quantum gravitational field. And here you are considering, okay, let's say that I have a model for quantum spacetime or a quantum gravitational field. How would a quantum system behave when living in it? And possible effects that people have been considering are modifications in the uncertainty relation, similarly to what I was discussing earlier concerning the black hole and Heisenberg uncertainty principle put together. People have been considering violations of CPT symmetries, fundamental decoherence, which is what I'm going to discuss next. Also, possible violations of the Pauli exclusion principles. So the idea is that quantum spacetime properties may generate modifications in known properties of our quantum theory. Okay. So all these are very different areas that are all working somewhere between here and here in the parameter space. And before going to the decoherence, let me mention that at the moment there exists a mostly European initiative, but mostly, well, the funding is European, but is open to everyone, which is a cost action. So this is basically a network that funds meetings, scientific visits, and training schools, and all of that. And the goal is exactly to investigate the interface between high energy quantum gravity and gravitational effects in quantum systems. So it's about what I was discussing earlier. And well, here is a list of questions that we are trying to answer. I'm not going to read them all. You will you can look at the slide better when I post them. Here you also have the website. But yeah, I wanted to advertise it because for someone who is interested in quantum gravity phenomenology, maybe worth joining the network. This year we are every year we organize also a training school, and this year will be about low energy tests of gravity and quantum gravity. So it might be interesting for some of you. And yes, as a last topic, I wanted to mention this possibility of studying how quantum systems, how the dynamics of quantum systems is modified if we account for quantum properties of space-time. Okay. So this is a slide from, I think, the first lecture that we had, where I was discussing how you describe symmetries in a non-commutative spacetime, and in particularly, I was using exactly a quantum formalism for describing the action of symmetries. So I just wanted to put this here again so that you can recall what we were talking about. In particular, I was mentioning that you have symmetries described by Hopf algebras instead of Lie algebras, and this allows you, for example, to describe the action of, say, translation generators on two particle states, and these can be deformed once you're deforming the symmetries and other properties. I'm not going to discuss it all again, but this was just to remind you. So within this framework, so where you are describing the symmetries of a non-commutative spacetime in terms of a Hopf algebra, then because you have this Hopf algebra, this will enter in the description of the dynamics of quantum systems. And a way to see this is you look at the usual evolution equation that you use in quantum mechanics. So the time evolution of your density matrix is given by the commutator between the density matrix and the Hamiltonian of your system. This is standard quantum mechanics. But then in the same spirit as in this slide, where you're generalizing the structures from the Lie algebra to the Hopf algebra, you realize that this commutator in the Hopf algebra language is what we call adjoint action. You don't need to know the details of what this is. You just need to know that when you consider the adjoint action, this knows about, for example, the coproduct of your symmetry generators. And when you put it in your evolution equation, you will get a modified evolution equation, okay? Here now you have that the time derivative of your density matrix is given by, instead of the commutator between the Hamiltonian and the density matrix itself, is given by the adjoint action of the time evolution operator on the density matrix, which is just the generalization of the commutator. And we studied what happens when, as algebra of symmetries, you consider the algebra of symmetries of the Kappa-Minkowski non-commutative spacetime, which is the model that I was discussing also in the last lecture. Again, this is just a hypothesis. We have to start from somewhere. We started from that model because we know it well. And we know that we have already characterized the symmetries of that model as a Hopf algebra that we call Hopf algebra. Now, since we are looking at quantum systems, we have to do a Galilean limit of that. And in the Galilean limit, you get a modification of the time evolution of operators that takes this form. You use this to write the adjoint action that is here, and then you get a modified evolution equation for the density matrix of a quantum system. Now, what I said before was to motivate this. Now let us look at what this is telling us. So we have one contribution, which is the standard contribution coming from the commutator. And then we have a correction term. Now, this correction term turns out that has a structure that is the structure that people had been developed independently to describe the coherence of quantum system. So to describe the coherence, one evolution equation that you can use is the Lindblad equation that is valid within a relatively large set of assumptions, so it's quite generic. So once you get something like this from your modified symmetry model, so from namely from your non-commutative spacetime model, what this is telling you is that the non-commutativity of your spacetime is inducing the coherence on the quantum particles that live on this spacetime. And in fact, you see that here you have the kappa scale, which is the non-commutativity scale of your spacetime, or the deformation scale of your symmetries. Well, you can show, for example, to show that this is describing the coherence, you can show that, for example, you have an increasing entropy of your system. This is just one way. But anyways, what I wanted to comment on is that we found the coherence in this specific case. However, people have been studying the coherence induced by either gravity or quantum gravity for many years. And it seems to be a quite general feature, the fact that the interaction between quantum system and gravity generates the coherence of the quantum system. So again, in the spirit of trying to understand what may be general features that we should expect from quantum gravity, one of the general feature may be the fact that quantum systems tend to decohere due to quantum gravity effects, even just to classical gravity effects. This has been also studied. Just very last slide for today. Starting from that evolution equation, you can describe, for example, the evolution of a free particle. For a free particle, the density matrix, you can write it in the momentum basis in this way. And what you will get is that the evolution of the density matrix has a damping term for the off-diagonal elements. So delta E refers to elements of the density matrix with the P different than Q. And this is exactly what the coherence is. So you have the off-diagonal elements in your density matrix that tend to zero. You can compute how fast this decoherence happens, and this is given by the decoherence time. And you can use this to put a limit on what is the mass of a system that can be observed in a quantum state. So what will happen is that in general, the larger the mass of a system, the more difficult it will be to keep it in a quantum state. And within this model, what happens is that you are not able to observe quantum properties of the system if the system has a mass that is larger than the scale kappa. And the scale kappa, as I mentioned, is the quantum gravity scale. You can think about it as the Planck mass, for example. So this would give you motivation for saying that you cannot have quantum particles that have a mass larger than the Planck mass, which is relevant. Again, going back to studies where you are trying to detect the gravitational field of a quantum particle. The larger the quantum particle in mass, the easier it is to measure its gravitational field. If you have some the coherence mechanism of this sort, again, this is a toy model, so one would need to understand how general this is. But if you have a decoherence mechanism of this sort, then you know that you will not be able to have quantum particles with mass larger than the Planck mass. So you would need to improve how sensitive you are to the gravitational field, because you know that you cannot have particles with too large a mass. And yeah, I think this is all I wanted to say. This is a general summary. So the general summary is that we have very good news, which is that nowadays we are able to test Planck scale physics in different areas of our parameter space. We have seen different examples concerning different regimes. And the hope is that we will start slowly collecting information about what happens in all these different areas. And this will provide us information about all these complementary regimes and help us build the full quantum gravity theory. I have I promised you some references to reviews on the different topics. I still want to add a few more, so I will put these slides online on my website later today or tomorrow, and they will have a larger list of references. And I think I can stop here, so we also have time to take some questions if there are any.
Fantastic, Giulia. That's great. Any questions? Please go ahead and ask.
Yes. Giulia, please could you show again the last slide with the references?
Exactly.
Yes.
I don't do that too.
I mean, this is not complete yet. I still want to add a few more things, but yeah, you can screenshot this for the moment.
Giulia, just it so happens I'm right here.
Oh, very nice.
I'm just pulling out right here, right?
I have a question, Giulia, but let me thank you for the class. Is very, very, very nice. And thank you very much. My question is about the measurements of the fine structure constant you have shown. It's very impressive that you obtain for L a value of the order of the Planck scale. But is there any other possible explanation for these deviations in the measurements?
So that I know of, no. I mean, people are trying to see whether there is any systematic measurement error in this measurement that would explain why this is off with respect to this one. So I don't know. Also, I mean, this is not work that I have done directly, so it might be better to ask directly the authors of these works, because surely they have been thinking about it more. But that I know of, no, this is a puzzle that people are trying to understand.
If I may add, apparently the discrepancy in the G-2 in the muon measurements Apparently, it has something to do with the QCD corrections, at least in the theory part, right? Experimentally, yeah, the two different.
But this is different. This is not the muon. This is
Yeah,
the
this is
electron.
Is, oh, the one here you say
Yeah.
something like the
G minus
This
two.
is the electron G minus 2,
yeah, okay.
which has no problems when measured by
With
particle physicists.
Fantastic.
Any other question?
And
I see one in the chat. What is actually causing the coherence? You mean in this model that I was discussing? So what is so in this case you have the coherence basically because you have a deformed time evolution. And the time evolution is deformed because you have space-time non-commutativity. So you have, in order for all your time evolution, space translation symmetries to be compatible with your non-commutativity, you have to deform them. This is what we also discussed in the previous lectures. And here you have a modification of time evolution that is causing this decoherence. So you know that in general, I mean, the coherence in general is very well studied. We know that, for example, a quantum system has decoherence when it interacts with an environment. This is well established and observed. So this, the coherence effect that I'm talking about would be some additional decoherence on top of eventually the interaction with an environment. Similarly, when people have been studying the coherence due to interaction with the gravity, that would be when you are looking at gravity as some environment with which your quantum system is interacting. Now, in this quantum spacetime, there is no environment properly described. But what you see is that the effect of your quantum spacetime is to act on your quantum system as if it was an environment.